SwayamPrabha. Digital India. Educated India.
सहनावतु सहनौ भुनक्तु सह वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
This will be lecture number 12, mechanical measurements. What we will be doing in this lecture is to continue our discussion on thermoelectric thermometry, or the use of thermocouples for the measurement of temperature. Towards the end of the last lecture, we were talking about some practical aspects, and before we get back to these aspects, let us just recapitulate to some extent what we did there. We in fact described the basic thermocouple circuit. We also looked at the temperature variation in the wires. We will again do the same thing here, and because this has some practical implications, and having done that, we will look at some more laws of thermoelectricity. There are 3 of them. These are very useful in the practice of thermoelectric thermometry. Then we will look at what is called the practical thermocouple circuit, and we will discuss briefly the use of a junction box, and we will round off the lecture with probably 2 problems depending on the time available. So, in the next slide, I am showing the simple thermocouple circuit, which was in fact also looked at in the last lecture. It consists of 2 wires. The positive wire is shown as P and the negative wire as N, and there is a junction between the positive and the negative wire, which is maintained at the temperature T subscript M. This is the measuring junction. And if you remember what we have said earlier, there should be a reference junction. In this case, it is the junction is between the N wire and the P wire. So, the measuring junction between P wire and the N wire, and if you go in the same direction between the negative and the positive wire, there is a junction which is maintained at the reference temperature. In practice, the reference temperature is usually going to be the ice point, and we will come back to this ice point and how to maintain the ice point later on. Invariably, when you have a thermocouple circuit, you have to make connection to a voltmeter or a potentiometer, and that requires, as you see here, 2 junctions are formed immediately. There are 2 extra junctions, one between the P material and maybe the wire which goes to the voltmeter is a copper wire, this one, and similarly from the P material here I will have another wire which probably is a copper wire. So, you see that as soon as we have a connection to the voltmeter, we have 2 extra junctions. In fact, we wanted only the junction at temperature Tm, the junction at temperature Tr, but because of the connection to the voltage measuring instrument, we have 2 more junctions. In case these 2 junctions are at the same temperature, you see that this is a positive wire, this is also a positive wire, and there is a connection between a positive and a copper. There is a junction between positive and copper, and similarly another between positive and copper, and we will see a little later that these 2 junctions are not going to affect the measurement. How? and why we will come to a little later on. So, this is the simple thermocouple circuit which one can think of to make the measurement of the temperature Tm with the reference temperature being given as the ice point or 0 degrees Celsius. So, in the next slide I am showing the nature of the temperature variations in the wires. In this particular problem, you remember there was the measuring junction at Tm, the reference junction at Tr, and there was also the junction, the two junctions which were formed by connecting it to the voltmeter. We had a junction temperature of Ta. So, I have shown these two temperatures levels. Tm is this is the temperature axis. I have got Tm, this line corresponds to Tm, the intermediate line corresponds to the temperature Ta, and the reference temperature corresponds to Tr. There are three temperature levels in this particular circuit. And if we look at what is going to happen in the wire connecting the various junctions, the length of the wire may be quite large. If I use a very thin wire and a very long wire, it is likely that the wire will cool off in a short length from the measuring junction. It is Tm here at this measuring junction. Within a short distance, it is going to cool down to the temperature Ta, which is we can take it as the ambient temperature. This is so for both the positive wire as well as the negative wire. So, both of them have become more or less cooled to the temperature equal to Ta. Therefore, the region which is subject to temperature variations along its length, along the length of the wires, is confined to a short region close to the junction, as you have seen here. This is the junction. Very close to that, there is a variation in the temperature along the wires, and therefore, if you remember the discussion we had earlier regarding thermoelectricity, thermoelectricity manifests whenever there is a temperature variation along the wire, okay. And in this case, the temperature variation along the wire is limited to a region close to the junction, and therefore, the active thermoelectric material is very close to the junction. So, that is what I am trying to get at. And similarly, near the junction at the reference temperature Tr, again there is a warming up from the junction to the ambient. You can see here it is warming up to the junction from the junction temperature to the ambient temperature, and similarly the positive wire. So, both of them. In other words, much of the bulk of the wire away from the junction is at a uniform temperature equal to Ta. And if you remember what we have said earlier, if a thermoelectric material is at a uniform temperature, there is no thermoelectric phenomena which is taking place. Therefore, we can see that the thermoelectric phenomena which is taking place is limited to a small region close to the reference junction, another small region close to the hot junction. This is very important, because we are going to now propose using a different way of connection. If you see here, bulk of the wire is at a uniform temperature, and therefore, there is no need to connect by using the same wires as the thermocouple wires. We can in fact use some other wire. We can use extension wires, so called extension wires, which are usually made of the same material as the thermocouple wires, but of lower quality, or we can even use copper wires uniformly away from the junction. So, you have a junction, and a very short distance away from the junction you have a wire connected to it, which is either copper wire or a extension wire, so that we save on the cost of the thermocouple wire. Otherwise, if the thermocouple is, let us say, wires are 10 or 20 meters long, depending on the application, we will have to use 20 meters of highly expensive thermocouple material. It is not, it is wasteful, because it costs a lot of money, and there is no point in doing that, because bulk of the length of the wire is actually at a uniform temperature. So, this is very important to understand. Now, apart from this, we have some 3 thermoelectric circuit laws which are going to be useful in the practice of thermometry, thermoelectric thermometry. One is of course the law of homogeneous materials, which simply says that a thermoelectric current cannot be sustained in a circuit of a single material, homogeneous material, however it varies in cross section by the application of heat alone. It is very important. If it is a uniform material made of the same homogeneous material, whatever may be the shape, size of the cross section and so on, if you simply apply a temperature variation like that, nothing is going to happen. The second law is called the law of intermediate materials, which plays a very significant role, as you will see in a little while from now. It simply says that the algebraic sum of the thermoelectric forces in a circuit composed of any number of dissimilar materials is 0 if all the junctions are at the same temperature. This is a very important relationship, and we will go back to the thermoelectric circuit and explain it a little later. But what does it mean? It means simply this: I have two circuits. The first circuit I have got the negative material, then I have a material C which is connecting the junction at Tm to another junction is formed between C and the positive material, but this entire thing is at the same temperature Tm. This junction as well as junction and the entire material here is at the uniform temperature. And now I have got the reference temperature junction here, and I am going to measure the voltage between this plus wire and this plus wire. So you can see that there are three junctions Tm, Tm, but there is a third material C, and the relationship we just had was any number of dissimilar materials is 0 if all the junctions are at the same temperature. That means because these two junctions are at the same temperature, this material being there is of no significance. That means I can remove this material C and look at the circuit shown on the right. I have got a single junction at temperature Tm, Tr, and I have got a negative wire and the positive wire, and this particular thing is missing. These two are equivalent. That means that whatever potential difference I am going to measure across the terminals in the first circuit is exactly the same as the one I am going to measure in the second circuit. That means that this extra wire which is at a uniform temperature equal to Tm is not going to affect the measurement. And if I go back to the previous figure here, you see that this is the temperature Ta, this is the temperature Ta, there is a third material, and you see that this is exactly what we have in the second law which we explained in the earlier slide. So that means that the presence of these two extra junctions is of no significance. It is as though the voltage indicated here is only because of Tm and Tr, and these two junctions were absent. If it were not so, we would never be able to use a thermocouple circuit, because it would be very difficult to construct a thermocouple circuit to measure the temperature. So with this, let us look at the another important law, which is called the law of successive or intermediate temperatures, which is very useful, and I am making a small sketch in the next slide to explain this relationship or the law. Suppose I have two junctions T1 and T2, and I measure the electromotive force across the junctions, the E1. I have another arrangement in which the junctions are at temperature T2 and T3, and I measure the voltage or the electromotive force as E2. Now, if the junctions are at T1 and T3, here T1, T2, T2, T3. So now I make it T1, T3. The electromotive force appearing across the junction E3 is the sum of these two, sum of E1 and E2. Very important relationship. Let me just see how it can be used. For example, suppose I do not have a nice reference point. I am not able to have a nice reference point. Suppose this is the temperature I want to measure, T1. T2, instead of being the ice point, I have got the room temperature. Okay. Let us assume that the room temperature is measured by a third thermometer, some other thermometer which is easily accessible to us. So I know the temperature T2. I know the temperature T2. Now, if you connect the thermocouple between T1 and T2, which is room temperature, it will give you some output E1, and the T2 room temperature with respect to, let us say, T3 I consider the ice point, for example. T2 with respect to ice point will give E2. Actually, what I should do is I should add this E1 to E1, I should add E2 to to find out what is the output of this thermocouple if this were at the measuring junction temperature and this were the ice point. Therefore, to find out what is the correct temperature, all I have to do is to add whatever is going to be obtained by this arrangement between the room temperature and the ice point. This can be done by, of course, looking up a table. You look up a table of thermocouple, whatever material you are having for the thermocouple, you look up the table, put T2 equal to the room temperature, T3 equal to ice point, this directly comes from the table. You are going to measure this E1 in your experiment, then you add this E1 plus E2 and you will get the value E3, and this E3 will now be the correct value of the electromotive force, which you should see, go back to the table, find out what is the temperature corresponding to E3, that is the correct temperature of the junction T1. So, the law of intermediate temperatures is an important relationship which helps us in actually performing thermometry. So, the three laws of thermometry or thermoelectric materials, the first law which said something about the fact that you cannot have any thermoelectric effect in a homogeneous material, whatever may be the area of cross section, however it varies, by applying heat you are not able to get anything out of that. The second one is we had the law of intermediate materials, the presence or absence of the material, intermediate material is not going to be felt as long as the junctions which are extra junctions which are formed are at the same temperature. And the law of intermediate temperatures helps us in finding out what will happen if I do not have the reference junction at the ice point, but at some certain temperature. I can find out by this use of this law of intermediate temperatures the appropriate value of E3, and therefore, I can find out what is the appropriate temperature. So, with these three laws, I am going to propose the use of a practical thermocouple circuit, because the practical thermocouple circuit actually requires the application of the three laws which I have just now proposed, which we have looked at. These three laws are going to be used here. Let us look at how it is done. We have the P and N material, positive and negative. Sometimes I use plus and minus, sometimes P and N, it means the same thing. One junction is at temperature Tm, and I have the other junction at the reference temperature Tr, N and P material. These are, this is P and N, this is N and P. This is very important. The junction must be between P and N here, and when you go round, it should be from N to P. This is very important. But what I have done is, I have connected a copper wire between here and here, a copper wire between here and here, and also a copper wire between here and here. So, now when I connect these extra copper wires, you see I have a new one more junction here. If you want, you can call it junction number 1 extra, junction number 2 extra, there is the junction number 3 extra, 4 and then 5 and 6. 6 extra junctions have been formed by connecting the copper wires as lead wires. Instead of taking the same wire all along, I could have done that. That is what I did in the simple thermocouple circuit. Here I am deliberately using copper wire. And if you look at the temperature variation, the temperature Tm here, Ta here, most probably all this material from somewhere very close to the junction is all at the same temperature Ta, that is the ambient temperature. Similarly here, therefore, the P and N materials have variation of temperature along their length close to the junction here, and therefore, why waste the material P far away from it. Similarly, for the junction at the reference temperature. Therefore, I am saving a lot of high quality thermocouple wire by substituting it with copper wire. Copper wire is available in good purity and also uniform quality, and it is much cheaper compared to the thermocouple wires, maybe a factor of 25 or 50, that is the cost ratio. So, the advantage of using a practical thermocouple circuit is that I am going to substitute the P wire by a copper wire, N wire by a copper wire. Sometimes what is done is, instead of copper wire, I will use the what is so called extension wire, same P wire, extension wire, which is not necessarily of high quality. That means that the purity and other requirements of the extension wire will be less than that for the thermocouple wire. So, I might even have, instead of this copper wire, I will have P wire made of less quality wire, and similarly here I may have N wire, which is a extension wire, same composition as the wire here, but not of equal purity or manufactured with the same care and so on. So, that I can use less expensive extension wires instead of the copper wire, that is also possible. The advantage of using less expensive junction wires is that most probably the performance of that material will be similar to the P material or the N material, as the case may be, and because the temperature variation is very little in that wire, any inhomogeneity in that is not going to materially affect the temperature movement. And you can see here I have got again a voltmeter connected using two junctions, and if these two junctions are at the same temperature as these are, all these extra junctions which are formed, 6 of them, if they are at the same temperature, or at least these two are at the same temperature, these two are at the same temperature and so on, we can guarantee that there will be no extra voltage developed due to thermoelectricity, and therefore, the voltage measured here is purely due to the temperature Tm and Tr. That means, I am equating the practical thermocouple circuit is exactly the same as the simple thermocouple circuit. We had only one junction, another junction, all wires of the same P and N material. This is exactly equivalent to that, electrically equivalent to that. That is very important, because of the temperature variation along the lead wires is confined to regions close to the junctions, and that is in fact the important reason. Sometimes what we do is, in order to make sure that these extra junctions which are formed are at the same temperature, these are going to be connected to a large block of material, which is a highly conducting material in terms of thermal conductivity, and all these terminals are going to be connected onto lugs on that material, of course properly electrically insulated, but they are all tied onto the same material, which can in fact be kept at a constant temperature by, for example, circulating cooled water and so on. A junction box is made by, in fact I will just make a simple sketch of a junction box, so that we understand what we are talking about. So, what we have is a large piece of material like this, and you might even have, it may be connected or it may be cooled block, for example of copper or aluminum, and we have all the junctions here, something like this, and you connect the wire onto this and possibly put a screw, something like that. So, the advantage of this is that all these junctions, all these, they are after all going to form junctions, are at the same temperature. So, they are all at the same temperature. The advantage is that we are now making certain that all the wires which are connected to the blocks here, terminal blocks here, are at the same temperature, and therefore, no net thermoelectric effect. That is the important thing. So, we do not have any net thermoelectric effect because of the lugs which are now all at the same temperature. Now, to continue with the discussion, let us look at, if you remember the simple thermocouple circuit, we have a measuring junction, you can see here we have a measuring junction, we have a reference junction, and the reference junction has to be maintained at a constant temperature equal to the ice point. So, we require an ice point apparatus or something which will provide the ice point, and it can be done by a simple arrangement like this. What I have got here is a large vessel. Normally we use a thermos flask, double walled thermos flask. Inside that I have got a long tube, you can see the long tube here, into which I have put the thermocouple wires, and there is a junction which is formed right here. This black thing is the reference junction, and it is immersed in a liquid which is a conducting medium. For example, I can use mercury, or I can use some oil, something which is going to have a good contact between the thermocouple and the medium, and the medium is now in the tube, which is completely immersed in a this blue colored thing here is a crushed ice water mixture. As long as ice and water coexist together, that means ice and the water mixture, crushed ice and water is formed, and as long as the ice and water mixture is present inside this vessel, the temperature is going to be the phase change temperature corresponding to 0 degrees Celsius. Therefore, the temperature of the entire mass here is 0 degrees, and if this tube is immersed totally into it and the reference junction is kept at the bottom, the chances are that the entire thing is going to be at the ice point. So, this ice point cell or ice point reference here is going to provide one reference junction for use with our thermocouple circuit. So, of course, the question now is, if you have a large number of thermocouple temperatures to be measured, let us say T1, T2, T3, T4, etc., each one of them will require a reference temperature which is given by the ice point. So, do we provide one ice point for each one of them, or can we provide a single ice point reference? So, that question is answered by looking at an arrangement which is possible, and here I have shown many hot junctions with a single reference junction, and I also have shown a junction box. You can see here I have got measuring junction 1, 2, 3 and 4. I have just taken 4 here, you could have any number, sometimes even hundreds of them can be used, and I have got the positive and negative wires coming from the junction connected to a junction box. This long thing is a junction box kept at a uniform temperature by the arrangement which I indicated earlier. And from the junction box I take copper wires, all these extension wires are copper wires, and then they go to another junction box, come switch. So, these are the junction box points, and there is a switch which will connect any two of these terminals to the rest of the circuit. So, let us look at, for example, if I were to connect this wire through this switch to this wire and this wire through this switch to this wire, what will happen is there is a copper wire, there is another copper wire, these are two, all these 4 points are on the selector switch which can be kept at the same temperature. Therefore, all these junctions are at the same temperature, these two junctions also. Then this is connected to one ice point reference, the minus plus here, again a copper wire and connected to the voltmeter. So, by using the selector switch, usually the selector switch is a very expensive equipment. It consists of a rotary switch, even though it is shown here as a long vertical thing here. Actually, it is usually a rotary switch with 16 or 32 or 64 terminals available for us, and by rotating the thing I can select these two or these two or these two and so on. Therefore, what I do is, when I want to take the readings of T1, T2, T3, T4, I will go through 1, 2, 3 all the different positions and note down what are the corresponding electromotive force which is going to be indicated by the voltmeter. Okay. One cycle will mean I go from 1 to 2 to 2 to 3, 3 to 4, note down 4 readings, and again I am ready to start this if the temperature is varying with respect to time. Therefore, here by using a selector switch which is a rotary switch, most of the time made with gold contact, so that the contact is very good. So, we are able to use a single ice point cell with several hot junctions to measure the voltages one by one by selecting each one in turn and then putting them together. We are able to get the measurements of several junction temperatures using a single ice point as well as a single voltmeter. This is very important. The advantage of using a single voltmeter is that the error in measurement of various quantities is the same, because we are using the single instrument. If we use different instruments, the calibration between the different instruments also will come to a picture, whereas here there is only one instrument I am using and the error is limited to the error of one instrument. So, several interesting points will come out of that if you look carefully. I do not want to give all the information. The student should learn some of these things by looking through and understanding what are the principles involved. In fact, if you look at the sketch, all the three different laws of thermoelectric circuits which we talked about earlier are all applicable here. They are all applicable here, and in fact we have several junctions have been formed. We are seeing to that all the junctions are at the same temperature by using the junction box concept. We are using a good selector switch, which is also usually a very bulky item, whose temperature will remain more or less uniform throughout. So, these are all some of the things involved in this particular measurement. So, to cut short the discussion, or to summarize what we have done till now, we started with thermoelectric phenomena. We discussed the Kelvin relationship, and then we talked about the relationship between the temperature and the output of a thermocouple circuit. We talked about either a table, lookup table, or you could think in terms of fitting a polynomial, and then we looked at both the simple thermocouple circuit and the practical thermocouple circuit using the three laws of thermoelectric circuits, and we also used the information that the temperature variation in the materials is confined to regions close to the junctions. Actually, the main point here is that the thermoelectric phenomena is not a junction phenomena. You will see that when we talked about the thermoelectric effects, the Seebeck, the Peltier and the Thomson effect, you see that the Thomson effect is actually continuous all along the material of the wire. The Seebeck effect is simply a combination of the other two. So, there is a relationship between the three of them, the Seebeck and the Thomson and the Peltier. The Peltier is something which happens near the junction, whereas the Thomson effect is taking place all along the length of the wire. Therefore, it is not correct to think in terms of the thermoelectric phenomena happening at the two junctions. No, it is happening all over the place. The question is, can we confine it to a region close to the junction, and that is in fact what is going to happen in practice, because the wires are very thin and usually they are very long, and because they are very long, they are going to move, they are going to be in the laboratory space, and the laboratory space is a uniform temperature. Therefore, it will cool to that temperature, and therefore, the confining the temperature variation to close to the junction is an automatic phenomena which takes place, and therefore, we are able to practice thermoelectric thermometry by using an arrangement which is shown in the figure. So, let us look at what are the other possibilities. We have several things which you can do, and let me explain before I come to the thermopile arrangement here. Let me just briefly explain using the blackboard. Let us look at the possibilities. Can we amplify the output? If so, how do we do that? If you remember, a single thermocouple, the output is in the microvolt or millivolt range. This is well known, we have already seen this earlier, because 1 degree Celsius gives about 40 microvolts for a K type thermocouple. In fact, K type thermocouple is one of the most sensitive even that provides only about 40 microvolts. Other thermocouples will provide less than this. So, if you use a single thermocouple, resolution is going to suffer. Resolution is poor. Or another way of saying that is that I must have very sensitive voltmeter to measure small temperature differences. So, if delta T is small, we need very sensitive voltmeter. So, that is the problem. Now, can we improve this situation? For that, let us look at what are the possibilities. Suppose I put two thermocouples in series. Okay, this is a junction T1, this is positive, this is negative. Okay. So, I want to increase the output by, of course, you have to have, this is what you have. This is one single thermocouple. We have already seen this. This is single. Suppose I do the following. Suppose I take several junctions. So, I am going to connect like this. So, these are all at T1, and let us assume that these are at TR. So, I am going to have a plus wire here, minus wire here, a plus wire here, minus wire here, and so on. And of course, I am going to take the connection from here and I will connect it to a voltmeter. So, I have got here 4 junctions T at same temperature and 3 junctions plus these 2 junctions, because these 2 entire thing is at a uniform temperature, and because this is made of a thermal material, if you use the law of intermediate materials, you can see that this junction and this junction together is like one junction. So, I have here 4 hot junctions and 4 cold junctions, all in series. That means that I am going to get the output, if this is V, this will be 4 times V is the output. This is output is equal to V. Single hot junction, single reference junction, I am going to get voltage equal to V. I have got 4 here and 4 cold junctions, as I explained just a while ago. These 2 together form one cold junction. So, there are 4 cold junctions, I get 4 times the output. That means that I am able to get a bigger output. For example, instead of 40 microvolts per degree, I will get here 160 microvolts per degree. So, there is an advantage. So, with this background, let us look at one of the applications, and it is called the thermopile. What is the thermopile? Thermopile consists of a large number of hot junctions and a large number of cold junctions. In this case, I have shown it in the form of a circular arrangement. So, I have got the hot junctions are all open circles and the cold junctions are all the blocked circles, and there is a shading ring. Yes, what the shading ring is doing is to prevent the heat from being communicated to the junctions which are in the shadow. One of the uses for this particular thermopile arrangement would be, you have, let us say, solar energy falling on these junctions. Because of the solar heat which is falling on them, these junctions will get heated compared to the other junctions which are in the shade because of the ring which is surrounding it. These are at a lower temperature, all the black dots are at a lower temperature and they are all in series. In this case I think I have about 15 or so junctions. So, 15 times the voltage will be developed, and what this measures is a large output. If the output for each thermocouple pair is only 40 microvolts as I just said, you will get about 15 times that, 15 times 40, about 600 microvolts, which will be a sizable amount. So, the junctions which are shown with the open circles are illuminated junctions and the others are shaded junctions. In fact, we have also indicated here another use for thermometry. If you remember, we were talking about measurement of temperature and suddenly we have shifted our emphasis. Here I am talking about measurement of solar energy. So, actually the heat flux or the flux from the sun can be directly converted to the increase in the temperature of the junction, and this is proportional to the amount of heat which is falling on it, and therefore, I am able to measure the solar flux using essentially a thermocouple or a thermopile in this case. Thermopile because a large number of thermocouples are in series. What we did earlier was to increase the output. We can also do the following. We can have a differential thermocouple. What is a differential thermocouple? It measures directly the temperature difference between two junctions. Where do we use it? Why do we use it? We will just look at it. So, I have two junctions, one at temperature T1, the other junction at temperature T2 instead of the reference temperature. I am not using a reference temperature here. I am using two junctions, one at a higher temperature and the other one is at lower temperature. So, plus minus, and this minus is coming here and then plus. So, between the two plus wires I am going to measure the output, and this will be the output due to the temperature difference between the junctions T1 and T2. If you remember the law of the third law which I proposed, in the third law I had T1 and T2, it is like T1 and T reference minus T2 minus T reference. So, what you get here is nothing but T1 minus T2, all right. You can work it out in your mind. So, this arrangement is going to give you directly the temperature difference. What is the advantage of this? Suppose I have a fluid flowing through a tube and it is losing heat, let us say. It is entering at temperature T1 and after going through a certain length of the pipe, it is going to come out with a temperature T2 which is very close to T1. That means that maybe 2 or 3 degrees variation is there. I can measure it in two different ways. One is I can measure T1 separately by using the thermocouple and a reference junction. I can similarly measure T2 separately using a reference junction and its point and this measuring junction. Now, I get two values from the table, one corresponding to this temperature, the other corresponding to this temperature. Then I have to take the difference between these two quantities. That means that the error in the first measurement and the error in the second measurement, if you remember the propagation of errors, in this case there are two measured quantities and the error of each measured quantity T1 separately, T2 separately is going to affect the temperature difference because of the propagation of the error. If you measure directly T1 and T2, you are not going to have that problem. Therefore, whenever we are measuring very small temperature differences, as in the case of a fluid which is flowing through a tube and getting heated and losing heat or getting heated, if the temperature rise or temperature drop is a small quantity like 2 or 3 degrees or even 5 degrees, you can measure the difference directly instead of measuring the two separately and taking the difference. There is another advantage. If you are measuring the temperature difference between two quantities which are very close to each other, the thermocouple is almost a linear device. That is a great advantage. Suppose T1 is 35 and T2 is 38, 3 degrees, 3 into 40 microvolts, that is what you are going to get. So, directly you can convert the temperature difference, the potential difference directly to temperature difference by simply multiplying by using the Seebeck coefficient at around 30 degrees, 35 degrees, whatever value it is, you can obtain that. So, the advantage of a differential thermocouple is there are many. One is it reduces the error in a quantity when you want only the temperature difference, not each temperature separately, as in a flow where temperature difference is to be measured. Also the advantage is that the thermocouple is more or less linear in a small range, and therefore, I can use a constant value for the Seebeck coefficient, and without looking up into a table I can directly measure the temperature very accurately. In fact, the difference thermocouple can be used with an amplifier also. Suppose I take the difference between these two signals, put it in an amplifier, I can amplify by a constant factor. Maybe I can use an amplifier with 100 amplification, 40 microvolts will become 40 into 100, 4000 microvolts, and it becomes a very large value. So, I can measure it very easily, without much difficulty, and there is no reference junction. There are only two junctions, the difference directly being measured, the great advantage. So, with this background, I will try to see if I can give one or two examples. In fact, I had two examples in mind, maybe it will be possible, maybe not. Just before we go to the examples, I just want to make something known to you. The thermocouple tables are available from the following website. It is www.temperatures.com, and you go there and put tctables.html. I think I will show a different way. You can see better, www.temperatures.com/tctables.html. This is a useful link. If you go into that, you will be able to download all the tables you may require for calculating temperatures based on the measurement of the voltages. So, with this background, let us take a look at the example. So, the example I am going to take is the following. I will call it example number 11. No numerics here. I am just going to explain how to. I am going to use a differential thermocouple arrangement. Differential thermocouple as a calibration device. Suppose I have a standard calibrated standard reference thermocouple which has been obtained from commercially available source, and I have what I will call as individual thermocouple this is supposed to guarantee some performance index. For example, what we will be doing is, table is available. For this thermocouple, a table is available. The manufacturer has guaranteed that a table is available, and you can use the table for this purpose. For this I do not have. Question is, I do not know what it is. So, how do we go about calibrating this individual thermocouple with the help of the standard reference thermocouple? For that, what I am going to do is, I am going to make a circuit like the following, exactly like what we had. A differential thermocouple, this is standard, this is the individual. These terminologies are normally used by people working in instrumentation. This is standard reference thermocouple, and this is the individual. And now I am going to measure the potential difference across these two junctions. That means that this is plus, minus, minus, plus, this is plus, this is plus. So, this is at these two I am going to put constant temperature bath, whose temperature can be varied, but both of them are the same temperature. Both junctions are at the same temperature. And I can in fact measure the temperature also. What is the common temperature? I can measure by using the standard reference itself directly. I can make the measurement of the temperature, common temperature to which the two junctions are exposed by using the standard reference thermocouple, and I can also make the temperature, the reading of the difference between the two thermocouples. If the standard reference and individual are exactly alike, V will be equal to 0 for all t. If the two are in agreement, because at any time I am making the measurement, both are at the same temperature. That means I do not expect any voltage difference, but if the individual thermocouple is not behaving exactly like the standard, the V is non-zero if there is a difference in the thermocouple. So, if I make a small plot like what I am going to show in the next slide. So, I am going to make a plot like this. This is the temperature of the bath I can start with some value T1, T2, T3, T4, etc. On this I am going to plot delta V maybe in microvolts, because the two are made of the same thermocouple material. I am expecting very small departure, I am not expecting very large departure. Therefore, maybe you may have 100 microvolts here and maybe minus 100 microvolts here. The difference is only very small. Of course, in terms of a K type thermocouple, this will be something like 2.5 degrees. If you remember that 40 microvolts is per degree. So, at T1 the two may not agree, I may get a point like this. At T2 the error is actually like this, here the error may be like this, and so on and so forth. So, I can roughly say that the difference between the two thermocouples is such that the error distribution or the error variation with respect to temperature is given by a curve like this. So, this can be used as a calibration device, because I can add or subtract, as the case may be, the voltage indicated here as a correction. So, the values may be used as a correction. What do you mean by correction? I am going to use the standard reference table is there already. That table gives you some value. In that table, whatever value you get, you add or subtract the value shown here and go back to the table and find out what is the temperature. So, I am going to use the individual thermocouple in the measurement. I am going to find out what is the output of this individual thermocouple, and corresponding to each, then I can find out what is the error between the individual thermocouple and the reference by having a calibration chart like this, and I am going to use this as a correction to make a correction in that, and therefore, to improve the accuracy of the measurement of the temperature using the individual thermocouple. If I have got, let us say, hundreds of thermocouples which I am going to use in the laboratory, I may not be able to calibrate each one of them like this. I will take for probably a few of them at random, maybe 5 or 10 thermocouples at random, find out how each one of them performs with respect to the calibration like this, and then maybe average out. Because normally what we do in practice is to make thermocouples in the laboratory using the wire obtained from the same manufacturer, from the same batch. That means that most of the thermocouples are similarly behaving, and therefore, if I take a few of them from this lot and I calibrate some of them and then try to find out what is the average error and so on, that may be a good idea. So, the calibration need not be that you calibrate each individual thermocouple. Of course, for highest accuracy you have to do that, but in the case of ordinary laboratory practice, I may take a few of them and calibrate them and then assume that this is an average of the behavior of all the thermocouples and use it. So, a differential thermocouple has become useful another way now. First I said it is useful when you want to measure a small temperature difference, and also said that the thermocouple is more or less linear in this small temperature range, and therefore, I can easily measure the output. Third one is I can use it for calibration purpose. So, simple differential thermocouple has at least 3 different uses which you can think of. So, in the next lecture, lecture number 13, I am going to continue and give the next example, and then once having done that, I will try to look at what are the sources of error in thermocouple thermometry. Thank you.